Hello, I am Samuel Santos. I will be speaking for excuse me, homework assignment for excuse me, for class the 10th of July. So today we'll be going over the biomechanics for strength and conditioning. Now, to begin, we'll be going over levers. Excuse me. Now, levers in the biomechanics useful for this class come in three, as I have drawn right here, come within three classes. There is the first class lever, the second class lever, and the third class lever. Here, let me erase this just for right now because we will get back to it. Now, the first class lever has, sorry, for levers, there will be three parts we have to focus on. We have to focus on the muscular force, simplified here by F, the fulcrum, which is the actual axis of which the action occurs, and then the resistive force, simplified here with R. So F will be muscular force, the fulcrum will be represented by these dots, and the resistive force will be represented by R. So for the first class lever, we will have our force, our muscular force, F, with the fulcrum in between with the resistance force. So it will go muscular force, fulcrum, resistive force. Now on the opposite, and divide here with this little angle. On the second class lever, we'll have our muscular force on the very distal end of the lever with our resistive force in the middle and our fulcrum being at the end. Our third class lever is the opposite. While my my fulcrum is here, also at the distal end, is going to be fulcrum, muscular force, resistive force. The fulcrum, muscular force, resistance force, with the resistance force being on the most distal end of the lever. Now, these can be found throughout the body. Right here. As some examples, my neck, our necks, will be a good example of a first class lever. This is because we have the muscular force of, we'll just say, our trapezius muscles, and then our resistive force being the actual weight of our head, with the fulcrum being right here at the first vertebrae. So if I am to turn my head this way, on our second vertebrae, sorry again, I do mean our first vertebrae. So we have our muscular force right here, our first vertebrae right here, working as our fulcrum, and the resistive force of the weight of my head. Now, when the muscular force is utilized, I will be turning up. This is because my muscular force is acting on the fulcrum, acting on the resistance force, resulting in neck extension. Now, our second class lever, a little bit more confusing, but it will be an actual calf raise. And for this note, I put calf and toes. Sorry for the misspelling. However, why this is because the way our legs work, our lower legs operate, is if this right here would be the calf, and this being the foot, sorry, this needs to be straighter for the demonstration. This being the foot, our fulcrum would be right here on the distal end of the on the toes, or like on the distal end of the toes. Now the muscular force will be pulling up, and the resistance force will be our body weight here on the heel, pulling down. Now, when the muscular force acts onto the resistive force to the fulcrum, we cause that heel to lift off the ground. This is an example of our second class lever because, as we stated here with our muscle force, resistive force, fulcrum, we see the same pattern here with the muscle force being the calf, our resistive force being the weight of our body and our heel, and our fulcrum being the toes, causing the actual lifting of our calf raising, with the fulcrum being on our toes. Now for our third class lever, I have here as our bicep brachii being in flexion. Now, why would this be considered a third class lever? Well, if I can erase this lovely drawing, our bicep brachii sit on top of our, if the fulcrum is our elbow, here. So this would be the humerus. Sorry, let me switch colors. If our humerus is located right here, I know red being a funny color to choose for bone, with our humerus being right here, and our forearm, or we'll just say our radialis, being right here, our fulcrum will be right here at the elbow. Well, our biceps don't sit directly in line with the elbow. They sit on top and insert right here onto the radius. Now, our muscular force is pulling right here, and our resistive force is actually right, our resistive force is the weight over here. Now, if we can look at it this way, we see that it's our fulcrum, our muscular force, and then our resistive force. Here. Our resistive force. So, given that it goes the same pattern as our third class lever, it will be classified as such, because same here as is fulcrum, force, resistance. Here is the same thing, fulcrum, force, resistance, and when the force acts on the resistance through the fulcrum, it results in that flexion upward. Now, to talk about the mechanical advantages of each, right here, the mechanical advantages, as we're discussing the mechanical advantages of each, the mechanical advantage over here for the first lever is actually pretty dependent on where the fulcrum is located. To better explain, let's move on to the second and third lever. The second lever has a mechanical advantage of greater than 1. This means that because of where everything is, it's pretty efficient at lifting heavier loads with much less effort, given that the resistance is situated in the middle of the fulcrum and the muscular force. The muscular force now takes much less effort to actually lift a greater resistance, given that the mechanical advantage is greater than 1. Now, the third class lever is that while it does take much more effort to overcome the torque of the resistance force, it does allow for greater ranges of motion. Interestingly enough, most levers in our body, apart from our calf and toes as pointed out for calf raise, are third class levers. Even right now with our bicep brachialis right here, given that our muscular insertions are by some senses of the word inefficient, as to where it takes more effort to lift the resistance, the great advantage of having a mechanical advantage of less than 1 is that we have greater range of motion. Given that our insertions do not overcome our hand for greatest ease, we do have our greater range of motion, given that our biceps brachialis, for example, inserts right here on the proximal end of the radius. So, given that I can just lift up my arm, even though it may take more effort to lift a heavy load or heavy resistance, I do have a greater range of motion and speed when doing so. Now this will bring us to our next Now to bring us to our next component of this biomechanics for the strength and conditioning, it'll be to explain the changes in difficulty or changes in effort to throughout the range of motion of a activated fulcrum or an activated flexion, or the changes of resistance within a movement, even when the weight stays the same. This has to do with moment arms. If our, excuse me, we'll take the bicep flex, or our bicep brachialis flexion as an example. As we establish, the muscular force is distal to, or is next to the fulcrum, medial to the fulcrum, but the resistance still distal to the effort. We'll be using this, our elbow, as our axis, and this line as our moment arm. No, I'm sorry, as our resistive force. First, we must explain what a moment arm is. The moment arm is the distance, simplified, is the distance represented here by the red cap right here on the marker, is the distance between the resistance and the fulcrum, and I'm sorry, the axis. So when right here, the perpendicular distance, when right here in full extension, or in about full extension, the actual moment arm, it's not difficult to hold this position because the axis and the actual, the moment arm, given the perpendicular nature of it, with the force of resistance right here, almost in the same line of the axis. This would mean our moment arm is much smaller, and as our joint angle changes, even in the small lift, in about a quarter of the way there, the moment arm has greatly changed. So right here, it's a very small moment arm, the distance between the weight and my elbow, to a small lift, the distance between the weights perpendicular to my elbow has changed greatly. The greater the moment arm, the greater torque this is applying to my axis. Sorry here. And as I get farther, the hardest part of the lift, as we will say, is the farthest part, or is the longest moment arm between right here, the red cap, and the axis being my elbow, is now the farthest it will be, which is why our lift will feel the heaviest at 90 degrees here. And as we bring that moment arm smaller, distance between here and here, the perpendicular distance between here and here, now it gets easier, as my muscular force is able to easily overcome the torque that this is placing on it, that the resistance is placing on my arm. One more time. I'm starting right here, very small moment arm, increase in distance, the greatest increase in distance at 90 degrees, given that this is the farthest away from the axis. And as we get closer, it becomes easier once again. Even going down to the eccentric, much harder, now much easier. Now in this assignment, we've been asked to calculate some calculations, so I have them written out here, and is to apply the principles of force being equal to mass times acceleration. Acceleration in this case being replaced by the gravitational acceleration, 9.81. Now, excuse me. Now we also use the concepts of, now we need to find from force output to power output, and then we're going to compare between two lifts, a deadlift of, as I have right here, a deadlift of 150 kilograms, which is our mass in this case, from a height of 0.3 meters or 30 centimeters, from in the time of a 2.5 interval with, and we were asked to calculate what the power is. Now we do the same thing for on the opposite side, right here, a power clean with a mass of 75 kilograms from a 2-meter height with a time of 0.5 seconds. Now, to begin, let's begin by finding out our power output with the numbers of 150 kilograms to 0.3 meters to in a 2.5 second interval to find out our power. We begin with finding out our force, which is mass times acceleration. Here, acceleration is going to be used by gravity, 9.81 meters per second squared. To find out, we take our 150 kilograms and multiply it by the 9.81 to get to our number of 1,471.5, here represented by newtons. Now that we have our force being y here, we're going to plug it into our working equation, or work equation for force, force multiplied by distance. Sorry, I understand this seems like a B here. Our force multiplied by distance. For here, we're going to take our 1,471.5 and multiply it by our 0.3 meters to arrive at our 441.45 here calculated by joules, measured by joules. Now that we have our work, we can plug it into our power. Our power, we're going to divide our work divided by time. In this case, our work, as we calculated, the 441 and 45.45 being divided by 2.5, where we arrive at our power being 170, sorry, or 176.6 here calculated by watts. So this right here will be our power output for our deadlift. Now we're going to do the exact same thing over here to calculate our power clean power output. So for our power clean power output, we have a mass of 75 kilograms and 2 meters off the distance traveled with a time of 0.5, very fast person. So we plug in all the same numbers as before. For force, we plug in our mass, our 75 kilograms, multiplying by gravity again, 9.81, to arrive at 700 and, to arrive at our 700, excuse me, we have to arrive at our 735.75, to which we're now going to multiply it by the distance traveled, our 2 meters, to arrive over here for our excuse me, to arrive at our work being 1,471.5. Now we can take our work, plug it into our power equation, and divide it by our 0.5 seconds. Here, divided by 0.5 to arrive. Sorry, I had to make a slight correction. I had put the wrong number here. So we're going to take our work right here at right here. We're going to take our work at 1,471.5, dividing it by 0.5 to get to our power at 2,943. Calculate in watts. Seeing this, we are now easily able to tell that and I'm sorry, I apologize, I've been saying power clean instead of snatch when this is a snatch. We can see that the snatch put out a lot more power than our excuse me, than our deadlift. Now, finally, knowing that now the snatch puts out much more power than our deadlift, we are going to, which would be a great application here in the real world, especially in the world of athletics. We were also asked to discover the movement velocity, or velocity, for both lifts, using the same numbers as before. So, velocity here is determined by, I have it written down right here, velocity is distance over time. Now, velocity is distance over time. Now, the distance for the deadlift, again, was 0.3 meters, with our time being 2.5 meters. Simple enough. To find our velocity, we take our 0.3 and divide it by our 2.5 to arrive at a velocity right here at 12 meters per second. Now, on the other side, we have to find our velocity over here for our excuse me, snatch. Given that we have a greater distance at 2 meters, we're going to divide our 2 meters by our time of 0.5 seconds. Now 2 meters divided by 0.5 seconds will be a 4 meters per second for our velocity. I'm sorry, I had misspoke on the deadlift. Instead, I had accidentally read 12 meters per second is 0.12 meters per second. Now to recite what we've done, we've discovered the power output of the deadlift being over here at 176.6 watts, with the power of the snatch being greater at 2,943 watts, to a joint to see that the snatch put out much more power than the deadlift. Now, when we discovered our movement velocity, we saw that, again, right here, the snatch is moving much faster than the deadlift here, which you could probably see, meaning that you could probably see that the deadlift was using a lot of effort, which he was able to get it, and he was able to use as much strength as possible, while the snatch was done with a lot of power and a lot of speed. Now we see that how biomechanical principles can be applied to strength and conditioning. Thank you. I am Santos, again speaking for my homework assignment for July 10th for strength and conditioning. Thank you.